Jai Hind everyone, myself Sandeep Yadav, Assistant Professor CSC Department. Today I am going to deliver a lecture on functional dependencies and its various types and inference rules. It is a part of unit number 3 of the subject DBMS being taught to AKGEC student in 5th semester. So this is the outline of the today's lecture: functional dependencies, definition and type of FDs, inference rules. Next is closure of FD set and closure of attribute set. So let us start with the topic functional dependency and its type. So let there be a relation R having n number of attribute A1, A2 up to An. Now consider the following example. The student table is there. Now in this example we are seeing that marks are determining grades. So marks determine the grade. This table is having 4 attributes: roll number, name, marks and grade. As we are seeing that marks determine grades. So one attribute is determining other. The attribute that determine other is the determinant and the other attribute is known as the dependent. So let us generalize the definition. Let attribute and x and y are the two subsets of the attributes of the relation R. The values of x component of a tuple uniquely determine the values of y component. Then there is a functional dependency from x to y, and this is denoted by x determine y. That is, one value of x will determine one value of y. That is the meaning of the functional dependency, that one value of x will determine the one value of y. Now this x can be a single attribute or it can be a composite attribute depending on the situation. Now let us see how to diagrammatically represent this functional dependency. So there are various representations. First, there is an attribute x which determines y. So diagrammatically we will represent this in this way also: x and this is y. This arrow edge shows x determine y. Now next representation is when x is composite, means x is having two attributes x1 and x2 which is determining y. So let us see how it determines. Two arrows will come from x1 and x2 and combinedly they will determine y. Next, x is determining y1 and y2. So this is how x we are representing as how x is determining y1 and y2. As example, consider the following relation: account having the following attribute: account number, balance and branch. Now account number can determine balance and branch. So there is functional dependency from account number to balance and branch. This can be denoted by account number determining balance and branch. Now various types of functional dependency. The functional dependency is of 3 types basically: full functional dependency, partial functional dependency and transitive functional dependency. So first of all we will be discussing the full functional dependency. In a relation R, the attribute B is fully functionally dependent on A if B is functionally dependent on A but not any proper subset of A. that is A determines B, but no subset of A can determine B. Example, roll number, semester and department determine SPI. We need all these three things to determine SPI. Okay. Now the subset of this should not determine this one. Next is partial functional dependency. In a relation R, the attribute B is partially dependent on A if B is functionally dependent on A as well as only on any other subset of A. For example, enrollment number, department name determine SPI. Now, we are seeing that there is also an FD, enrollment number determine SPI. Now, a subset of this is also determining SPI. So, there is partial functional dependency, that is the subset of A is determining B, then that is the partial functional dependency. The third is transitive functional dependency. In a relation R, if attribute A determine B and B determines C, then A determines C, that is C is transitively dependent on A via B, that is the transitive functional dependency. Now, let us see in this table, this subject faculty table having the three attributes subject, faculty and age, having some entries. Now, here subject determine faculty and faculty determine age, then we can say that the subject determining age. Next is trivial functional dependency. X determines Y is trivial FD if Y is a subset of X. See, FD is trivial if and only if the dependent is a subset of X. For example, roll number, department name and semester determine roll number. So, this roll number is a subset of this. This roll number is a subset of this portion, X portion, that is the FD is trivial. Non-trivial FD, X is determine Y is non-trivial FD if Y is not a subset of X. For example, roll number, department name and semester determine student name, right? So, these determine student name and this student name is not subset of any of these. So, that is the non-trivial FD. Next are the inference rules regarding the functional dependencies. See, there are total 6 inference rules. First 3 rules are known as Armstrong axioms or Rat axioms, where R stands for reflexivity, A stands for augmentation and T stands for transitivity. In addition to that, there are union rule, decomposition rule and pseudo transitivity rule. So, in totality, there are 6 inference rules that are used in functional dependencies. First is reflexivity rule, which states that if B is a subset of A, then we can say that A determines B. Second is augmentation rule, which states that if A determines B, then we can say that AC determines BC. Third is transitivity rule, which says that if A determines B and B determines C, then we can say that A determines C. Third is pseudo transitivity rule, which states that if A determines B and B determines C, then AD determines C. That is pseudo transitivity rule. Third is, now fifth one is decomposition rule, which states that if A determines BC, then we can say that A determines B and A determines C. That is the RHS has been decomposed. Next is, and the last is union rule, which states that if A determines B and A determines C, then we can say that A determines BC. So, these are the 6 inference rules that we are going to use, and in these 3, 1, 2 and 3 are Armstrong or rat axioms. Next is closure of set of attribute. That is, given a set of FDs, there are certain FDs that are logically implied by F. That is, with the help of given FDs, how many new FDs you can drive, that is the closure of set of FDs. For example, A determines B and B determines C, then we can say that A determines C by using the transitive rule. So, the set of closure of FDs that is logically implied is called closure of F, that is denoted by F plus. This is how to denote closure of set of FDs, that is F plus. Now, we are having, let us illustrate with a suitable example. Suppose we are having a relation R having the attribute A, B, C, G, H, I, and the set of functional dependencies are A determines B, A determines C, CG determine H, CG determine I, and B determine H. So, from that, how many FDs we are going to determine, that is known as the closure of set of FDs. So, clearly we are seeing that A determines B and B determine H. This means A determine H, that is the transitive rule. Next, say this one, that is after the application of transitive rule. Next is CG determine H and CG determine I. Then using the union rule, we can say that CG determine HI. This is how we are going to see it. Next one, A determines C and CG determine I. Then we will be applying the pseudo transitive rule, and it will be AG determine I. This one. This is by the application of pseudo transitive rule. See, we need to clearly see which FDs are to be selected in order to drive new FDs. So, there is little bit of logical thinking that, and that we have to use to drive the new FDs. Now, A determines C, then using augmentation rule we can say that AG determines CG, AG determines CG and CG determine I, then we can say that AG determine I. Now, again a new question is there. There is a relation R having these attributes A, B, C, D, E, F, and A determines B, A determines C, CD determine E, CD determine F, and B determine E. So, let us find out the closure. See, A determines B and A determines C. Now, applying the union rule, A determines BC first. Now, CD determine E and CD determine F, then CD determine EF second by the application of union rule. Third is A determine B and B determine E, then A determine E, that is transitive rule. Fourth, A determine C and CD determine E. This means AD determine E, pseudo transitive rule. A determine C and CD determine F, that is A determine F. This is again pseudo transitive rule. So the closure of F is F plus, and these FDs A determine BC, CD determine EF, A determine E, AD determine E, and AD determine F. Next is closure of attribute set. Now given a set of attributes, the closure of attribute under F is the set of attributes that are firstly determined by that attribute under F. This is denoted by attribute plus. So why we are computing the closure of attribute? So we are computing the closure of attribute to determine whether that attribute determines how many attributes. If determines all the attributes, then we can say that that is the candidate key. So in order to determine the candidate key for a relation, we have to compute the closure of attributes. From that we can compute the candidate keys. Now given a set of attribute, the closure of attribute under F is the set of all attributes that are functionally determined by A under F. It is denoted by A plus. This is the algorithm to compute A. See, step number 1, initially result equal to A, while changes to result do for each beta that determine gamma in F do begin if beta is a subset of result. If this beta is a subset of result, this one, then result will be equal to result union gamma, else result equal to result, that is the previous one, and will terminate it with end. Now let us demonstrate it with the help of an example. Consider the relation R having the attribute A, B, C, G, H, I, and it has the following set of FDs: A determines B, A determines C, CG determine H, and CG determine I, and B determine H. So we have to find the closure of AG plus. Let us see how to find out. So this is the algorithm that we are going to use. And now step number 1 is initially result equal to alpha, then here the result equal to AG, because AG is the attribute for which we have to compute the closure. Now first FD is A determine B. Now this A is a subset of result, so result equal to AG union B, that is ABJ. Next, A determines C, then this A is the subset of ABJ, the previous result. So in the result will be equal to ABG union C, that is ABGCG. Next, CD determine H, then CG determine H. This CG is a subset of ABCG, then include H in the result. Now the new result will be ABCGH. Next FD is CG determine I. Now this CG is a subset of the previous results, so result will be equal to previous result union I, that is ABCGHI. Now B determine H, and B is a subset of previous result, so then the result equal to ABCGHI. See, there is no change in result, so the closure of AG plus is ABCGHI, right? That is AG plus is the candidate key for the given relation. Let us demonstrate it further with one more example. given a set of FDs for relations schema R having the attribute A, B, C, D, E, A determine BC, CD determine E, B determine D, and E determine A. Find the closure of A for CD, for B, for BC, and for E. Let us determine it. Now, A determine BC, right? So, ABC is there, right? Now, B determines C, B determines D, then it is ABCD, and CD determine E, then the closure of A is ABCDE. So, this is a candidate key. Next, we have to compute for CD. Now, CD determine E, then CDE, from CDE union A, that is CDE A, right? And this A determines BC, so union BC, that is A, B, C, D, E. This is how we are driving this one. In the similar fashion, B determine D, so the answer is BD. In the similar fashion, we can compute the closure of BC and E also. So, this is also ABCDE and this is also ABCDE. So, here we are seeing that there are 4 candidate keys for the relation R, because the closure of 4 attributes is determining all other attributes. So, these are the 4 attributes in this particular relation which acts as a candidate key. Next, let us see what is an extraneous attribute. See, AB determines C and A determines C. Now, in A, B determines C, B is extraneous because C can be already determined through A alone, that B is useless. We get to rid of B. This is not at all required. So, B is a extraneous attribute. So, an attribute of functional FD is said to be extraneous if we can remove it without changing the closure of set of functional FDs. So, that is for the canonical cover. Let us find the canonical cover. Consider the relation R having the attribute ABC with a set of FDs. A determine BC, B determine C, A determine B, and AB determine C. So, we have to find the canonical cover, that is, we have to find the minimal set of FDs, that is irreducible set of FDs. So, what is the procedure? First, AB determine BC and A determine B, then this means A determine BC using union rule. So, we can get the rid of one FD itself, right? This FD is of no use. This is already covered here. Now, check if the resultant of deleting A from ABC is implied by other dependencies. Yes. B determines C is already present. So, set is A determine BC and B determine C. Next, C is extraneous in A determine BC. we have to check whether the B AC is logically implied by AB and the other applied FDs. So A determine B and B determine C. So that means A determine BC. So the canonical cover is only two FDs that are left, that is A determine B and B determine C. This covers the syllabus of today's lecture.